I hit the wrong, they moved the buttons around, so I keep hitting the wrong button. All right, so here we were talking about if it's not on the redox chart, maybe we can get some clues about its reactivity by analyzing its oxidation states. That's the whole point of this. All right, so let's take a look at what we had here. We will do some more examples for these. We talk about the little nuances involved in this. So this was the HCl, the homework. So what did you guys come up with for the chemical properties of HCl? Probably what chemical property stands out the most about HCl? Acid base. And as far as acid base goes, this contains both an acid and a base, right? Because normally we think of HCl as being a strong acid, but it contains both an acid and base. The acid is H plus and the base is Cl minus. But we know something about that base. Even though Cl minus is on our base chart, you saw it on our base chart, right? What can you say about Cl minus? It's very weak. It's so weak, we don't even label it as an acid. We'll just call it a neutral. So let's say you ran out of antacid at home. So you don't have any more antacid, but hey, you saw chloride. Chloride's a base. I'm just going to take a bottle of table salt and consume that to neutralize my stomach acid. Will sodium chloride neutralize your stomach acid because you saw chloride's a base, right? It's going to do nothing for your stomach acid. Why? Because chloride's a very pathetically weak base, right? It's so weak we don't even consider it a base. So we'll just call it neutral or N. H plus, this is a strong acid. Okay. And so we'll call that an acid here. And so what does it react with? It reacts with pretty much all the bases stronger than or equal to water, right? Well, it depends if it already reacted with water. Or Cl minus. All the bases stronger than Cl minus, but this is very tricky. Is HCl's at the bottom of the list. What if you're at H, or no, it's not at the bottom of the list. Where is HCl? Let's take a look at HCl. At the bottom of the list was HNO3. So here it is in the middle of the list, in the middle of the strong acid list, right? It's in the middle of the strong acid list, which you'd say the pattern. Okay, I know the pattern. The pattern is HCl will react with any base stronger than chloride, and you have the pattern right, except there's an exception. And that exception has to do with the blank effect. What was that blank effect? Its inductive effect is a big one. It's important, but not in this case. It's another effect. What was another effect that we were dealing with? The blank effect. The leveling effect. The leveling effect means all these bases here are the same. All these acids over here are the same. So we don't say any base stronger than chloride because these bases are the same strength as chloride. Well, you have to be careful because then you would say HSO4 minus might be able to pluck it, or this one. And you might say these won't, but these are all the same. So what we need to do is we need to drop down a little bit.
And that's only the ones above water?
Yeah, only the ones above water. And so what I'm going to say is H plus, will react with any base stronger than water. If I call this H3O plus, then it's already reacted with water. So H3O plus will react with any base stronger than, well, anyway, than water. But what I'm going to do is I'm just going to say H plus will react with any base equal to water or stronger than water.
Does that mean this leveling effect is the same on the other side for strong bases?
Yeah, the leveling effect is the same on the opposite side. However, it's a little bit more complicated. It's a little bit more complicated because of, and we're going to see this, so actually we're going to look at this in more detail, because of the amount of hydroxide that's produced. And also, we end up with two things. So if we do oxide plus water makes two hydroxides, whereas if we do hydride plus water only makes one hydroxide. And so already there's a big discrepancy in how much hydroxide is produced. The other thing is, some of these produce not only hydroxide, but they also produce another base. So when amide reacts with water, it produces hydroxide plus ammonia. Hydroxide is a strong base, ammonia is a weak base. And those combined will increase the amount of hydroxide. So we get the hydroxide from the strong base, and we get a little bit of hydroxide from the weak base. And so the total hydroxide is a little bit more. And so the basis, I was going to avoid talking about that because it's easier, rather than memorizing all these qualitative things, it's just easier just to grind out the calculation. And we're going to be doing calculations with these acids and bases to figure out how much. You know, like I said, acetic acid doesn't produce that much hydronium because it's a weak acid. Weak acids partially hydrolyze water. Weak acids partially ionize. And but you know, partially is qualitative. We want quantitative. We want to know how much. Is it 1%, 10%, 30%? And we want to be as precise as possible. And so we're going to do those calculations soon, actually. And so right now, why I'm going through this is, first you want to get a feel for what's going to happen, and then we're going to grind out the calculations, because oftentimes what happens is people get into the calculations and they come up with ridiculous answers. These answers are impossible, but they still turn it in. But if they just looked at it and said, oh, that's not possible, then they would have caught their calculator error. They made some calculator error, or they made some setup error there. And so we'll have a better idea. And also, you don't always want, sometimes somebody asks you, what's this or what's that. You oftentimes, you don't have time to say, okay, wait 30 minutes to an hour, let me finish the calculation, and then I'll get back to you. Sometimes they just want a qualitative answer in certain things. So, you should be able to do both, qualitative and grind out calculations. A lot of the calculations can be simplified tremendously. If we had to approach every single calculation the same, then that's a lot of work. But sometimes you say, okay, this is a strong acid that's going to react like this, and this is such a weak base, we were going to ignore it. But if you didn't know that we could ignore nitrate, then you'd be sitting there trying to do a calculation with nitrate in the solution and wasting a lot of time. Which still happens. I mean, I see some calculations that you look at, boy, they spent a lot of time on that calculation, but it's totally, unfortunately, useless. Okay, so that's what we have for acid base. So this one reacts with, this one pretty much reacts with, in this case, H2O and stronger. The reason why this one's a little bit of an exception is because H plus is so unstable. Do you recall I was talking about Coulomb's law? Coulomb's law has two factors in there that we look at. What are the two things we look at in terms of reactivity? The charge and the distance. Yeah. In other words, that distance is a measure or a proxy measure of the the bigger the distance, the bigger the distance, the smaller the distance, the smaller the distance between the centers, the smaller the atoms are, or the particles are. The bigger the distance, the bigger the atoms or particles are. So it's a matter of what we call charge density. You know, how much charge is packed into the volume. Small atoms, high charge density. Lots of charge packed into a small volume. Big atoms, lower charge density. Think about the charge density of this, H+. Let's compare that to lithium plus. H+, they say H+ doesn't exist. We use H+ all the time because it's shorthand. H+ AQ doesn't exist. Why? Because H+ would be way too reactive to exist in water as a separate entity. What happens is H+, what is H+ made out of? Well, it's H3O plus. This is the shorthand. H3O plus exists. There's no problem with H3O plus. But the problem with H plus is the hydrogen atom consists of what? How many protons? How many electrons? So if you get rid of that electron, then all you're left with is a proton. How big is a proton? Well, if the hydrogen atom, let's say, were about 1 angstrom, or let's say about 100 picometers in diameter, what would the proton be? What would the nucleus be? The nucleus is about how many times smaller than the atom? Like 1,000? Well, it's about 10,000 times smaller. So they say if an atom is the size of a football field, then the nucleus would be like a golf ball or something like that. And so, so what we're going to have is we're going to have a positive 1 charge concentrated on an extremely tiny volume, or in an extremely tiny volume. Let's compare that to lithium. Lithium has 3 protons, 2 core electrons, and 1 valence electron. If lithium loses that valence electron, then we're going to end up with this, where we have the 3 protons and then the 2 core electrons here and no valence electrons. How big is this? So now we have a +1 because the 2 electrons are -2 and then we have 3 protons. Now we got a +1. But how big is the lithium ion compared to a proton? Tens of thousands of times bigger. And so you can see that the proton is going to be extremely reactive. Extremely reactive. So reactive that it doesn't exist as a single entity. Really what this means is, this means hydronium. H3O plus, or higher derivatives of that. You know, I was talking about radon gas earlier. And radon's radioactive. And what radioactive elements have is they have an unstable nucleus. And so radon, part of that nucleus breaks off, a chunk of it breaks off. And you know what that chunk of nucleus that breaks off is? The chunk of nucleus that breaks off is an alpha particle. Do you know what alpha particles are made out of? Yeah, protons, neutrons. Any electrons? So, alpha particle, let me ask you this. Radon is radioactive. Is an alpha particle radioactive? Alpha particle is radiation, particle radiation that you get from radon. But is the alpha particle itself radioactive? No. The alpha particle is not radioactive. The alpha particle causes chemical damage. Do you know oxidizers that are more powerful than fluorine? I'll tell you an oxidizer that's much more powerful than fluorine. Fluorine's at the top of the chart, but you know You know an oxidizer that's much more powerful than fluorine? Alpha particles. You don't want to inhale alpha particles. That would be worse than inhaling fluorine gas. And the reason why is because it's a helium atom with both its electrons stripped away. So if we have a helium atom with both of its electrons stripped away, what is neutral helium? Neutral helium has 2 protons and 2 neutrons. And 2 electrons. Now you strip away the electrons, what are you left with? You're left with the nucleus. How big is the nucleus? Very tiny. And that nucleus is +2. The proton was +1 in a tiny nucleus. The alpha particle is +2 in a tiny nucleus. Can you see how electron poor this is? Helium is so unreactive, it doesn't want to lose its electrons. So helium is not a very good reducing agent. It doesn't want to lose, it's very stable in redox properties. But if you take these electrons away from helium, then you make an this is an extremely powerful oxidizer. And the damage comes because this is a gas, and you're inhaling this stuff that's going to oxidize your lung tissue. It's going to oxidize everything and cause damage, oxidative damage. Does that make sense? So this is extremely powerful oxidizer. And so it's not radioactive, it's just an extremely powerful oxidizer. And the radon gas, which is radioactive, is spitting out this powerful oxidizer as a gas. And then you inhale that radon gas and have subsequent chemical damage to you. So what we want to do is we just want to get bits and pieces of this chemical trivia, and then just hopefully we can remember enough of it that we can make predictions based on we've seen this before or other things. Okay, so let's go back to HCl. This is the acid-base properties. And so chloride's not going to react with anything. Okay, next what did you look at? Because HCl, what stands out are the acid-base properties, but what did you look at next? Redox. Okay, for redox, we have H+. What's H+? H+ is an oxidizer. What can it oxidize? Okay, so let's take a look at H+ here on the chart and see what it can oxidize. So here we have H+ here, or H3O+. H+ and H3O+ are used interchangeably. In redox, we prefer to write H+ because it's less writing. We don't want to have to write H3O+ all the time. It takes too much time. But what can it oxidize? Any reducer?
Stronger than lead.
Yeah. Equal to or stronger than lead. Good. That's exactly right. Now, how about chloride? What is chloride? Chloride's a reducer. Here. Is chloride a very good reducer? No. H+ is a moderate oxidizer, an okay oxidizer. But chloride isn't a very good reducer. But what will oxidize chloride? Or what will chloride reduce? What are all the species that will oxidize chloride? Or what are the species that chloride will reduce? Will chlorine oxidize chloride? No. So we need something more powerful than chlorine or less powerful than chlorine? More powerful. So what's more powerful than chlorine? Yeah. Lead 4 oxide. We also have lead 2 oxide. Lead 2 oxide is not enough, but lead 4 oxide will. What else? So if we dump in solid lead 4 oxide into hydrochloric acid, you know what's going to happen? We're going to start generating chlorine gas. What else? What's this called? Permanganate. If we dump in permanganate, there's already H plus present because this is acid. And so this is kind of important, this H plus. And the same thing here, we need H plus present here. Why do we need H plus present? If you look at these, there's H plus, H plus, H plus, H plus. What do all these H pluses have in common? Well, we look at the product side, you know what all the H pluses have in common? They form water. Water is very stable, and so that helps drive the reaction. But anyway, here, this is called permanganate. So we want to know certain ions like permanganate, chromate, dichromate, oxalate, acetate, those. If we dump in permanganate in here, we're going to generate chlorine gas. If we dump in hydrogen peroxide, we're going to generate ozone, fluorine. All those will generate chlorine gas.
You said H plus can oxidize anything equal to or greater than lead? Or...
Yeah, equal to or greater than lead. H2 is not enough. H2 is not enough for that.
Well, H plus.
Yeah. So what I meant by that is, if we look here, there are different ways of saying this. The only thing that could screw it up is when I was talking about the strong acid. This is a little unclear how I phrased that, but this one should be clear here. H plus, H2 is not enough. So there are two ways to phrase this. One, we need a reducing agent stronger than H2. Or two, we need a reducing agent equal to or stronger than lead. It's probably better to say a reducing agent stronger than H2 because there could be something in between the lead and the H2. So to cover your bases, I would probably say stronger than H2. That's safer. Because you remember, science, there's no scientific policeman, but there are a lot of scientific policeman volunteers out there, and they're going to be on you, What did you say? And you're going to get fingers wagged at you. Especially if you're starting out. And so the same thing goes for this. This list isn't comprehensive. There are a whole bunch of things missing from this. If you go in the appendix, you'll see gold in there, platinum, a whole bunch of other things, that aren't there. How do you dissolve gold? Let's say if I wanted to dissolve silver, it's easy. I'd just use nitric acid. If I wanted to dissolve copper, I'd use nitric acid. But hydrochloric acid would not work. Hydrochloric acid would not work at dissolving copper. Why? If I wanted to dissolve copper chemically, when I say dissolve copper, I'm not going to get copper metal, I'm going to get copper ion. And so it's going to be a chemical process. But HCl is not going to dissolve copper. And so copper would be a perfectly suitable container for HCl. So if I put my HCl in a copper container, no big deal. That's fine. Because here the H plus is not powerful enough to oxidize copper to copper 2. However, if I put my copper metal, if I try to use that same copper metal container for nitric acid, that's a disaster. That nitric acid is going to eat through the container here. And so we use that for these types of things here. Now, what if I use a gold container? what's going to eat through my gold container? I used to use gold containers and platinum containers because gold and platinum are surprisingly unreactive. If you look at ancient gold, it looks like brand new, right? It looks very lustrous, like from these whatever ancient buildings and wherever. I mean, the gold retains its luster. It's very hard to oxidize. But will anything eat through the gold? And so we'd use a chart like this. We'd find gold here and then figure out what would eat through the gold. So it turns out most things don't. So gold and platinum were I used gold, platinum, and I used a lot of ceramics like aluminum oxide. You know, aluminum oxide +3, -2, extremely strong lattice, very unreactive. Aluminum oxide they use it for sandpaper. You know, the little grit on sandpaper. It's aluminum oxide mostly. It's very hard. It's 9 on the Mohs hardness scale. Diamond's a 10. There are people working on getting, even harder materials. I went back. I worked at a group in UCLA, and I went back to visit them. Not too long ago, right before during the pandemic. Actually, no, right before the pandemic was the first. I made 2 visits. He was telling me what he was working on, my old advisor at UCLA, and he was telling me he's working on this super hard material. The super hard material to clean diamond cutting bit. So if you have a diamond cutting bit, for drilling wells or whatever, how do you sharpen it? It's already diamond. So you need something harder than diamond. So what's harder than diamond? Well, they developed a material that's harder than diamond. The only problem with this material is it's a crystal, and only one face of the crystal or 2 faces of the crystal are harder. So they have to orient it so that otherwise, if the crystal moves in a different orientation, then it's not harder than diamond, and it'll just be eaten away. And so, kind of stuff. But I thought, wow, that's really pretty interesting. Okay, so we say that any oxidizer is stronger than chlorine. So chloride is a reducer. Okay, so H plus is an oxidizer, reacts with reducers stronger than H2. Stronger than H2. Chloride's a reducer, and that reacts with oxidizers stronger than chlorine, Cl2. Chlorine's a great oxidizer. And so this is a pretty poor reducer. This is a moderate oxidizer, weak reducer, Okay, what did you get from metathesis properties? Okay. So HCl consists of 2 ions, the H plus ion. What ions do H plus like? H plus likes any basic ion stronger than, at least based on our chart. Let's take a look. Well, I'd like to say any basic ion stronger than water. But water is not an ion, but we can have ions that are stronger base than water, like trichloroacetate. So I could say trichloroacetate, but there's probably some anion that's stuck in between these 2. So this might sound a little bit strange, but we'll just say any basic ion strong, because Metathesis are ion combinations. So we're looking for favorable ion combinations. So we're just going to say stronger. Let me rephrase this. Any basic ion that is stronger is a stronger base than water. And so what are the ions that are stronger base than water? We have a huge list of them here. And that's what H plus likes. H plus also likes other things as well. But they're all kind of similar in a sense. Like there are certain rules in chemistry that you just obey, otherwise your lifespan will be shortened. And one of the rules is do not mix acid with cyanide salts. You know, mix acids with cyanide salts. What's going to happen? Well, if you mix acid with cyanide salts, let's say if I take HCl and mix it with sodium cyanide, what's going to happen? Well, this is double replacement, but the H plus likes cyanide. Well, cyanide's a base also. And when H plus and cyanide combine, they form hydrogen cyanide, which is a gas. And you don't want to breathe in hydrogen cyanide because it's also a lethal gas. And so this would be an example of metathesis reaction here. So like cyanide, but cyanide is also, like I said, it's a base. We don't want to mix it with sulfide salts too, because H plus loves sulfide. In fact, if I take two H pluses and I react it with a sulfide, I make H2S gas. H2S gas, did you know somebody died? I think it was in the last 10 years in Ventura from H2S. H2S occurs naturally there. It smells like rotten eggs. H2S smells like rotten eggs, but it overwhelms your olfactory sensors or whatever. It saturates them so you can no longer smell them. So you smell H2S for maybe like a minute or a couple of minutes, and then the smell goes away. That's very dangerous because this stuff is lethal at the part per billion level, which is very low. This happened at one of the oil wells there. So I guess there was some H2S gas that came out of the ground, overwhelmed the person and killed them. Also, I think the Mammoth Mountain or something, some skiers died from volcanic gases, but I think those were oxides of sulfur. I don't remember. Probably not H2S because H2S is a pretty good reducing agent as well. It's electron rich. H2O is not. These are little tidbits of information that you generate. H2O is not very electron rich, but H2S we consider electron rich. Now, what's the difference between H2O and H2S? This one is not electron rich. This is electron rich. Not electron rich. Why? So this is factual knowledge. This kind of factual knowledge we want to kind of correlate with something theoretical. And so what's the difference between oxygen and sulfur? What's one of the differences between oxygen and sulfur? Oxygen's breathable. Yeah, H2S is not breathable. That's for sure. The mass is different. That's true. But it's not the mass that kills you or can potentially kill you. What is it? The reason why this is considered electron rich and this is considered not electron rich is because of the size. Think of, if you're going to steal or take 2 electrons from an atom, you're the oxidizer, you're going to take 2 electrons from this atom. Is it easier to take the 2 electrons from a big atom, where the electrons are spread out over a bigger volume? Or is it easier to take it from a small atom, where the electrons are tightly held? From the big atom. So sulfur is a big atom. You got 2 electrons. Oxidizer comes along, it can easily pluck those off compared to oxygen, which is going to have a much harder time plucking those electrons off, a smaller atom. And so sulfides are normally thought of as good reducing agents because they don't hold on to their electrons that tightly. And the oxidizer can come along and take them. So I don't think it depends on the vents, volcanic vents or whatever. There's probably, a lot of, there might be oxygen. If there's no oxygen, then it could be a lot of H2S coming out of the look. So there are other, but these are all, this is a base. Is this a strong base or weak base? A strong base. You memorize 7 common strong acids, but you probably don't have the bases memorized, do you? What are the strong bases? The strong bases are the soluble hydroxides, the soluble oxides, the soluble sulfides, the soluble amides. All amides are pretty much soluble. Those are the strong bases. Okay, what anions does chloride like? Or not? It doesn't really like anions. Chloride likes cations. What cations does chloride like? Which ones?
Silver.
Silver cation? Yes. Chloride likes silver. And so if there's any source of silver ions, it could be like silver nitrate, silver acetate, it'll react. So we have the source of silver ions that we're going to form solid white silver chloride. This is a very common reaction in chemistry. It's precipitation of white silver chloride. Watch out for the silver ions though. Silver ions are a good oxidizer, and your skin is a good reducer. And so what happens is if you spill silver solution, like silver nitrate solution on your skin, it turns black, but eventually it will turn silver because you're precipitating out silver metal. When you precipitate out tiny crystals of silver metal in your skin, those tiny crystals absorb visible light, and so they look black. You can't wash it off. One time I had a student in Chem 4. The student had an important job interview right after lab. And the student came up to me and said, I've been washing my hands for 45 minutes and I can't get these stains off my hand. And I said, oh, I'm sorry, but you're going to have to wait until you shed that skin because it's silver, and it's in your cells, basically. But, they weren't very happy. They were really furiously pissed off because I thought I explained, silver nitrate turns everything black. Don't get it in your eyes. You're going to precipitate out tiny crystals of silver in your eyes. But watch out for this stuff. But anyway, we're talking about chloride. What else? What other cations does chloride like? Lead. Which lead? Lead 2 or lead 4 or both? Lead 2. Any others? Mercury? Mercury 1 or Mercury 2? Actually, Mercury 1. Mercury 2, we're going to precipitate. And so these will precipitate out. Actually, Mercury 2 will probably work okay. Will probably form molecular. And so these are, in terms of metabolism, these are the cations it likes. Any others? No. That's it. And so these would be the chemical properties for HCl. Now, the situation here is this. I only talked about one type of acid-base reaction. What acid-base, and this acid-base chart is only for what type of acid and base. This acid-base chart is only for Bronsted. But I should also consider what type of acid-base reaction. I should also consider Lewis. So that brings up an interesting point. Here. if they gave me my access. Do you notice the numbers to the right of on the right side of the chart? You know those numbers?
Yeah.
So we're going to do this. We're going to look at gold. And so let's see, this one. Okay, here. We'll take a look at this one here. The oxidizers on the right, the conjugate reducers on the, excuse me. Let me rephrase that. The oxidizers on the left, the reducers on the right, like our chart. Our chart has the strongest oxidizer on the top left, the strongest reducers on the bottom right. So if we look at gold, this looks like the best. Gold being oxidized to gold 3. So we need an oxidizer that'll oxidize gold to gold 3. This is 1.52 volts, we say, for this. And so let's take a look at our other chart and place that. You know, I wanted to look at the book's chart because there, I wouldn't have to do this. But we'll look. .52 volts places gold metal right above here. So gold metal is here. What kind of oxidizer do I need to oxidize gold metal? I would need something like hydrogen peroxide in acid. This is not household hydrogen peroxide. This is heavy industrial stuff. Ozone or fluorine. Okay, none of these I really want to work with. You know, the best oxidizer we have is nitric acid. One of the best. Is nitric acid enough to oxidize gold, which sits up here? No, it's not. It's not. And so what we can do is we can do some crafty things with this. And those crafty things are nitric acid doesn't have enough to oxidize the gold, but maybe we could help it along. You know, maybe if you see somebody struggling up the hill, you know, riding their bicycle up the hill, and you come pedaling by and it's easy, you might give them a hand and pull them up the hill, right? Well, the same thing. We might have a reaction that would never make it up the hill, but we might couple that with a second reaction that pulls it up the hill and then down the other side. Okay, so that's the case for gold. You know, dissolving gold has always been something that like metallurgists and others have been interested in. And so how can you dissolve gold chemically? This is not a physical dissolution process, this is a chemical. And so do you know how gold can be dissolved, or what the technique for dissolving gold is? Mercury, you can form an amalgam, you know, an alloy. But the technique for dissolving gold is this. Have you heard of aqua regia?
No.
Aqua regia means regal water or royal water in Latin. And so aqua regia is a mixture of nitric acid and hydrochloric acid in a 1-to-3 mixture. And so how does aqua regia work? And so let's take a look at the chemistry of aqua regia. So let's have some solid gold metal. And what we're going to do is we're going to take our aqua regia, which is going to consist of 1 part nitric acid, 3 parts hydrochloric acid. So 1 part nitric acid, 3 parts hydrochloric acid. 1-to-3 ratio. Okay, I'm not going to work out the balanced chemical equation here, but I'm just going to talk about how this works. So, interesting thing about this is this. None of these, the first thing you think about when you think about nitric acid is a strong acid, right? The first thing you think about when you think of hydrochloric acid is a strong acid. But neither of those is acting as an acid in this reaction. Do you know what nitric acid is acting as? Nitric acid is acting as an oxidizer. And do you know what hydrochloric acid is acting as? Hydrochloric acid is acting as a base, but didn't I just say chloride is a worthless base? Yeah, I did. But it may be a worthless Bronsted base, but it's an okay Lewis base. And so this is actually acting as a Lewis base in the oxidizer here. And so let's see how we would do this. Here. The first thing is to know what gold does in this. So the highest potential, okay, ignore this for right now. We'll talk about that in a minute. But the highest potential is going to be for this. Gold goes to gold 3. And so what we do is we look at the strongest oxidizer present and the strongest reducer present. And so what I'm going to do is I'm going to list the inventory of this. So the first step in analyzing this redox-wise is the inventory. Inventory means gold just consists of gold metal. Nitric acid consists of H plus and nitrate. Hydrochloric acid consists of H plus and chloride. And these are aqueous. Since these are aqueous, we also have water. And water normally doesn't react, but it can. If you have sodium around, water reacts. So we gotta include it because there's a potential it could react. And if there's a potential, then we don't want to miss that reaction. Okay, then we're going to label everything. Gold metal is a reducing agent. It can lose electrons to form gold. H plus is an oxidizing agent. Nitrate is an oxidizing agent in combination with H plus. So when we look at the chart, nitrate plus 4 H pluses plus 3 electrons. Did you see that on the chart? This is an oxidizing agent. Now, what happens if you don't have that H plus? So when I look at nitrate here, nitrate plus 4H plus 3 electrons yields NO in water. If I don't have any H plus, am I going to form any water? No. In fact, instead of forming waters, I'm going to form oxide. Oxide is going to be less stable than water. Oxide's a powerful base, more reactive. Water's a weak base, less reactive. That's one of the properties. But anyway, this is like, okay, if you're making cookies, let's say your cookie recipe calls for 3 cups of flour and 1 cup of sugar. If you don't have the 3 cups of flour, well, actually, let me make it the same, sorry. 1 cup of sugar, 4 cups of flour. So let's say I'm making cookies and I ran out of flour. So I'm just going to make it out of sugar. Is that going to work? No. And the same thing here. This is a recipe. So if I don't have any H plus here, will this recipe work? No. And so what that's going to do is it's going to change its rank. If there's no acid present, its rank is going to drop way down. So this is the reason why I gave you sodium nitrate. When you look at the chemical properties of nitrate and sodium nitrate, and you compare that with the chemical properties of nitrate and nitric acid, it's different. It's different because you're missing the H plus. In nitric acid, you have plenty of H plus. It's a strong acid. In sodium nitrate, there's no H plus, unless you dump some acid in there. If you dump some acid in there, then it's fine. It'll react the same way. So, eventually we'll be doing more here. But this is good because I have nitrate in combination with H plus here. And in fact, there's H plus over here as well. And so this is going to make it so I can have the proper recipe for this reaction to occur. Okay, again, what I was saying earlier is if I only had sodium nitrate, I don't worry about this as much versus nitric acid. And I don't worry about this as much because it's missing what? H plus. If I had sodium nitrate plus HCl, then I worry because now I have a source of H plus and I worry. So if I had sodium nitrate and ammonium chloride, I worry. So if I put in sodium nitrate with ammonium chloride, I'm worrying a lot. This is going to cause lack of sleep because ammonium is an acid and a reducer. It's a weak acid, but it's good enough to give H plus, but it's a strong reducer. So you worry. Okay, H plus we already talked about. Chloride is a reducing agent. Water is both. Water occurs on both sides of the chart. Water can be an oxidizer. It's a very poor oxidizer. In fact, where's water as an oxidizer? Water is at the very bottom of the list. Didn't I tell you the worst oxidizer was lithium ion? Yeah, I did tell you that. Water is not at the bottom of the list. They separated this into two charts. One chart for acidic neutral, the other chart for basic. And so water occurs in the basic side of the chart. What we have to do is we have to look at the number. So if water is an oxidizer, I look at the number over here. When I look at the number, it's minus 0.828. So remember that, minus 0.828. And then I go over here and I look, minus 0.828 puts it between these two here. So water belongs here. And where is that? That's between zinc and aluminum here. So let's scroll over. So what I did was I put these three dots here. Do you see those three dots? Those three dots are where you insert water. Water is a more powerful oxidizer than aluminum 3 ions, but it's a weaker oxidizer than zinc 2 plus. And so water belongs here in terms of oxidizing ability. Water occurs on both sides of the chart. Here. So for example, I see water here. This is water, but I'm missing a key ingredient. What's the ingredient I'm missing? Sulfur dioxide. I have no sulfur dioxide. I have water here, but I'm missing nitric oxide or nitrogen monoxide. I have water here, but I'm missing iodine. I have water here, and I'm missing nothing. So water is a reducer. But then I go on, and I see another water here. So which water do I pick? Should I pick these two waters or these two waters, and what's the difference? Why do I have two waters in there? To confuse you? Well, it ends up confusing a lot of students. They might pick the wrong one. So which one should you pick? The top water or the bottom water? The bottom. Why? Why should you pick the bottom? You're right. You pick the bottom, but what's the reason? Why you pick the bottom? Because it's stronger. It's stronger, but you're thinking, water, how can two waters be stronger than two waters? And the reason it's stronger is because of the products. When these two waters react here, what forms? Oxygen. When these two waters react here, what forms? Hydrogen peroxide. What's more stable, oxygen or hydrogen peroxide? Oxygen. So this is forming a more stable product, which means it's better. And so we're going to pick this, the more reactive. Then you think, why the heck did they put two waters there to confuse you? No, they didn't put two waters there to confuse you. It's just that these two reactions produce the same thing, product. Hydrogen peroxide, when it acts as an oxidizer, produces water. And oxygen, when it acts as an oxidizer, produces water. We need H plus for both of these, though. All right, so water occurs on both sides, so we call it both an oxidizer and a reducer. Then what we do is we take the strongest reducer on the chart and the strongest oxidizer on the chart. In this sense. And the strongest reducer would be something like chloride or water. But in this case, we want to pick gold. We want to oxidize this. Is what we want to oxidize, and we're going to oxidize it with this. Here. It's not going to be very successful. So what we're going to do is we're going to just pick the reactions off the chart here. So if I look at it, nitrate plus 4H plus with 3 electrons yields Na plus 2 H2O. So that's what nitric acid does, and we're going to write that down over here. So when nitrate oxidizes something, we go nitrate plus 4H plus 3 electrons yields NO gas plus 2 H2O liquid. If it's aqueous, I leave it blank. Okay, so it's going to get those 3 electrons. We want those 3 electrons to come from gold. So what I want gold solid to react to go to gold 3 ion plus 3 electrons. And so the overall reaction here is going to be this. When we do this, we've got to make sure the electrons cancel. So the electrons consumed is equal to electrons produced. Well, that works out nicely in this particular case. If it doesn't, then we have to multiply by some number. And so what we end up with is we end up with nitrate plus 4H plus gold. The electrons cancel, yields NO gas plus 2H2O liquid plus gold 3 plus. Now this is what we call an uphill reaction. In the normal reaction, we want to go downhill. So that is, we want to go from a stronger oxidizer to a weaker oxidizer. But this is going uphill because this oxidizer is stronger. And so we say that this is a stronger oxidizing agent. SOA is stronger oxidizing agent. And this is a weaker oxidizing agent. And so in other words, in terms of ranking, we're at nitric acid, gold 3 is way up here, way stronger. So it's going uphill. We need to go downhill. And so this just isn't going to happen. And then over here, we want to go from a stronger reducing agent. Now our hill is upside down. On the reducing agent, the top of the hill is at the bottom of the hill is at the top. And so we're looking at gold here. This is going to be a weaker reducing agent, WRA. This is going to be a stronger reducing agent. And so this is what we call uphill. Driving force should be downhill. So this doesn't happen. And so this is struggling to get up the hill. It's never going to make it. It's never going to make it unless it gets a pull. And you know what it's going to get a pull from? It's going to get a pull from this. Now, gold 3, is that an acid, base, or neutral? You think, heck, that's neutral, right? But it's not. It's a Lewis acid. And so the pull is going to come from this. If I take my gold 3, which is a Lewis acid, and then react that with chloride, and in fact, I'm going to put 4 chlorides on there. And so these chlorides are going to attack the gold 3. I'm going to make this AuCl4. Now, gold is 3 plus. Each chloride is 1 minus. So this thing has a negative charge. And this has a name to it. The name for this is called tetrachloroaurate, all one word, aurate, continuing all one word, Roman numeral 1, 2, 3. So this is the tetrachloroaurate 3 ion. This pulls it over the hill. So the job of HCl is this. We can dissolve it. HNO3 is not enough to get it up the hill. But then the chloride comes in to the rescue, and the chloride's going to do this. The chloride's going to attack the gold ions. And so let's say there's a violent collision and the gold ion is momentarily produced. That's so unstable, it's going to go back down the hill. So sometimes things can get knocked up the hill. Do you guys remember this curve, the Maxwell-Boltzmann curve? Of kinetic energy? There's a small tail of high energy. So let's say in one moment, boom, and a gold ion gets shot up pretty high up the hill. Obviously, it's going to roll back down. But let's say it gets shot up the hill, and then there's chlorides there to help it over. And so the chlorides are going to come in, attack the gold to form tetrachloroaurate 3 ion. Tetrachloroaurate 3 ion is very stable. This is called a complex ion. And this complex ion is formed from a Lewis acid-base reaction. Now, what are Lewis acids and what are Lewis bases? Lewis acids are electron pair acceptors. Lewis bases are electron pair donors. And so what happens here is this. We're going to have a chloride over here, and it's going to have 4 electron pairs, but one of those is going to be used to donate to the gold 3. When that happens, we form what we call a coordinate covalent bond. That is, the gold is not ionically bonded to the chlorine. Instead, it forms a covalent bond to the chlorine. We'll talk about the bonding a little bit, but mostly probably we'll save that for later. There's more room here. So this is still 3+. Both bonding electrons came from 1. Normally when we form a covalent bond, one electron comes from atom A, another electron comes from atom B, and they share. In this case, chloride supplies both electrons. We call that a dative bond, D-A-T-I-V, dative bond, or a coordinate covalent bond. And so this is a dative or coordinate covalent bond. Okay, there's still room for attack here, so 3 more chlorides come in. And so that was the first chloride. The second chloride comes in. Here. These 2 lone pair electrons are going to form a new covalent bond like this. A third chlorine comes in. And a 4th. And that's it. We stop at 4. Sometimes we can get 6 around there. Sometimes we can only get 2. There are different factors dictating how many chlorines will attack. In this case, only 4 chlorines attack. In other cases, 6 chlorines will attack. Obviously, we'd like to know the theory so we can predict how many chlorines are going to attack, but this is empirical right now. It's based on observation. And so here, we get a structure like this. Oddly enough, this turns out to be a square planar structure. You know, there are no lone pairs though. Vesper does not work for, these are called complexes, coordination complexes, chapter 24. Vesper does not work. Valence bond theory does not work for this. We need to use MO theory for this. And so VV theory fails for describing the shape of these things because there's no lone pairs here, and this square planar. So VV theory fails for complexes. You know, for complexes, we'd like to think of this as being sp3d2, sp3 sigma bond. No, that's not it. Okay. So VV theory fails. But this is enough to get it over the hill. And so this is the way aquaregia works. Aquaregia works by these 2 working as a team together to get the gold to dissolve. When the gold dissolves, it forms an aqueous solution of tetrachloroaurate 3. ions. You can recover the gold, so you dissolve the gold, you can get the gold back again by reversing it. This is a combination of redox, so we oxidize the gold, and Lewis acid base, we complex the gold. To reverse it, you got to break apart the complex and then reduce the gold back to gold metal using a reducing agent. And what reducing agents can you use? Anything, because gold 3 ions are powerful oxidizers. All right, what time do we go till? 12:55? 12:50? Okay. So I'm going, well, this is a complex. I'm supposed to start chapter 15 tomorrow. Let's look at some other complexes for right now. And go from there. So, maybe I'm going to start off with kind of an extreme example. The extreme example is this. EDTA 4 minus. So since I don't have that much time, well, I guess I got time left. I don't know how much I want to talk. Ethylene diamine. You know what ethyl means? Eth in organic chemistry. ET. Ethanol, ethyl alcohol. Eth. Two what? 2 carbons. So ethylene is this group. It's a CH2, CH2. That's called an ethylene group. And in the ethylene group, we have one more. Each carbon can have up to 4 bonds. So we have 2 hydrogens and 1 carbon, so that leaves a dangling bond here and a dangling bond there. You know what an amine is? An amine looks like ammonia. It's a base. And so if we look at ammonia, what's the electronegativity of hydrogen? Hydrogen's electronegativity is at 2.1. This ammonia is a good base because nitrogen will polarize the electron cloud towards it, like this. So it polarizes the electron cloud, which makes the nitrogen delta minus. And so that's a good base. Well, what if I take one of those hydrogens and replace it with what we call a methyl group? Methyl is CH3. How much does that change the electron cloud? So hydrogen has electronegativity of 2.1, carbon has electronegativity of 2.5. So 2.1 versus 2.5 is not a significant difference. And so what we say is it doesn't change the cloud that much, just slightly, Carbon's slightly more electronegative than hydrogen. But otherwise, the electron cloud kind of looks the same, which means that we have a lone pair here, and the delta minus will be about the same. Do you see it? It's going to be about the same. So this is our delta minus here. I'll try to draw it the same size, like that. And so what we say is this. Ammonia and this is called methylamine, are about equally as basic. They have comparable basicity. And so both of these are about the same in terms of base strength. Here. So this E stands for ethylene, D stands for diamine. So what we're going to do is we're going to put 2 ammonia-like nitrogens on there. But the nitrogens can either be bonded to hydrogen or carbon. It doesn't matter. They're both going to result in ammonia-like bases in the end here. And so we're going to have a lone pair here, and then these are going to be bonded to carbons. Here. Ta stands for tetraacetato. Do you know what acetate ion is? It's CH3CO minus. Well, this is acetato, or acetate. And so it's going to look like this. Rather than CH3, it's going to be CH2, C, O, O, and then there's no H, so it's minus. Yeah. And so we're going to throw 4 of these groups on here that are going to look like acetate. These terminal oxygens here with a single bond are all with a negative formal charge. Uh-huh.
Because we were learning about coordination compounds, and you mentioned like acetato, and you mentioned tetrachloro, like it's all kind of confused. Is there a way to like memorize?
Yeah. Yeah. You mean the how do coordination compounds, how do you name them, or how do they work, or? Yeah, there is. There's a simple way to memorize the names, but the first thing is we name the names of the things that attach the Lewis bases. Coordination complexes. What's this called? Chloride. When it's in a complex, we call it chloro. Bromide is called bromo. We have other things like this. Acetate is called acetato. And so the pattern is you just change the ending. This is chloride, we call it chloro, you know? We just change the ending to O. And so if we had something like this would be oxide. Oxide would be called oxo or oxido. Something like that. It's probably, hopefully it's still oxo. They're changing these names all the time. So that's part of it. The other part, the orate part, there's a systematic procedure for naming these, which we're going to talk about. In fact, that's our scope, is we want to learn how to name these things. And so there are a set of rules that we follow. And so we don't have to memorize much. The only things we have to memorize are these. These ones get special names. So H2O is not called water. You know what they call H2O when it complexes or forms inside a complex? We call it aqua. And so let me give you an example of that. Aluminum. Aluminum could have 4 waters stuck on there. And this whole thing would be 3+. And then we call this tetra aqua, double vowel, tetra aqua, aluminum, Roman numeral 3 ion. So this tetra aqua aluminum 3 ion. Tetra aqua aluminum 3 turns out to be a pretty good acid, Bronsted acid. These hydrogens, we'll talk about this later. These hydrogens turn out to be fairly acidic.
What makes something complex?
What makes something a complex? What makes something a complex is a coordination. There's electrical attraction. So,
in terms of categorization, sorry.
in terms of categorization, in terms of categorization, like in terms of categorization, it has to do with the mechanism of formation. So you have to know how it's formed and what the reaction is, and then you can determine if it's a complex or not.
You wouldn't necessarily know, like being able to determine unless you know a lot.
Right. So, for example, cyanide. Why is cyanide so poisonous? Because cyanide, in your blood, you have iron 2 and hemes. And these hemes are in hemoglobin in your blood. And the iron 2 has 4 things bonded to it. These are coordinate covalent bonds. These are bonded to, was it oxygen or nitrogen? And so let's take a look. And then we'll see that it forms a complex because of the mechanism in which it forms. I'm going to use some carbon monoxide because there's lots of images. Carbon monoxide. Oops. The fewer images of cyanide poisoning.
Did I say CH3 or CH2, correct?
It's CH2 because one of the hydrogens has to be knocked off, otherwise we're going to have too many bonds to carbon. And so if it were CH3 and you put it in there, then you have 5 bonds to carbon. You can't have 5 bonds because that would be an expanded octet, which violates the octet law for the second period element. All right, this is metal complex in blood. What makes this a complex and how can you recognize that this is a complex? And the way you recognize this as a complex is, one, the metal cations are Lewis acids. Why? Because metal cations are positively charged, they want negative charge. But the thing is, not all metal cations are Lewis acids. So for example, group 1 cations are not. Why? Because of the charge density. Group 1 are big, low charge. So in order to have a complex, you need a small, high-charged cation. Well, a small, high-charged cation could be like silver ions. Silver ions are small, even though they're +1. Those are high charge. And so we need a good charge density in order to fill. So we don't form complexes with sodium ions or potassium ions or those. Instead, what we form are what we call ion dipole interactions or hydration, waters of hydration, or solvated ions. You've heard of hydrated ions, solvated ions, ion dipole interactions back in chapter 15. Well, this is different. The aluminum, this is not waters of hydration. Those waters attack the aluminum. Why do they attack the aluminum? Because aluminum is a tiny ion with a 3+ charge, making an excellent Lewis acid. And so we're going to get a Lewis acid base reaction here. So the waters attack that. When the waters attack the aluminum, the waters aren't stuck on there. Normally, waters of hydration, we have an ion dipole attraction here. The ion dipole attraction is this, waters of hydration. And we can break those off easily. But that doesn't happen here. With aluminum, this lone pair attacks the aluminum ion, and it forms a coordinate covalent, or what's the other word? Coordinate covalent, or starts with a D, dative bond. So it forms a coordinate covalent or dative bond. Boom. So we get something like this. The water doesn't look like water anymore, does it? That water is covalently bonded to aluminum. It's weird because, metal and non-metal should form an ionic bond. No, in this case, it forms a covalent bond. This is a coordinate. It's a very polar bond, though. It's so polar, the inductive effect is huge. The inductive effect makes these hydrogens much more. The acidity of these hydrogens is much greater than the acidity of water. In fact, this tetra-aqua complex, you might have seen it before. get rid of it. Well, actually, gloves and use this. This tetra-aqua complex of aluminum is more acidic than acetic acid. Can you believe that? It's more acidic. Look at the iron 3. You know what we call this here? These waters are actually covalently bound to the iron 3. This is called hexa-aqua iron 3 ion, and hexa-aqua iron 3 is slightly less acidic than phosphoric acid, but more acidic than nitrous acid and hydrofluoric acid. You know, but that's a property of the complex. The complex itself forms from this, the metals being attacked. So iron's sitting here in your blood, and it's going to be attacked by Lewis bases. What are the Lewis bases that are going to attack your iron? It's going to be this weird molecule here. This is called the heme, which shows this carbon and other things. This is not a very detailed structure of the heme group. But let's say, let me see if I get a better structure of it. So you have this iron 2 sitting in here, and what you have are these nitrogens. These nitrogens are going to attack, these nitrogens with Lewis bases, lone pair, negative charge density, they attack the iron. So it forms 4 bonds here, and then another group comes in underneath this and forms a 5th. That leaves an open spot here for a 6th. You know what the 6th is? The 6th is not a very good Lewis base, but it works. The 6th is this. This isn't such a great Lewis base, but it's got a lone pair, right? And that lone pair can attack the iron 3. But it doesn't form a very strong bond. And so what we can do is we can get oxygen to form a coordinate covalent bond, but it's weak. It's a weak bond compared to nitrogen. Nitrogen form a much stronger bond. And so let's take a look at this. The O2 heme complex. We're all on Wikipedia, so we should look there. Come on. So we get a complex like this. So nitrogen has these 5 nitrogens. I mean, the iron has these 5 nitrogens, and then the oxygen comes along and complexes with it. And then eventually this is transported and the oxygen breaks off. But oxygen is not a very good Lewis base. There's much better Lewis bases. Do you know one exceptionally good, powerful Lewis base? One of the most powerful Lewis bases out there is cyanide. Cyanide's not a very good, it's not a very good Bronsted base, but it's an excellent Lewis base. So cyanide comes in here and forms a bond that's so strong it doesn't break off. If cyanide complexes with this, it's done for oxygen. Oxygen, there's no way oxygen is going to come in and break off the cyanide. And so you're pretty much going to asphyxiate yourself with cyanide. The same thing with carbon monoxide. Carbon monoxide is another powerful Lewis base. Carbon monoxide comes in, you're done. Oxygen's not getting in. So you got to get rid of that carbon monoxide on the heme. All right, let me stop here since I'm went over time. I wasn't planning to go.